All right, so today I'm going to be talking about how you can perform ocular correction when you're pre-processing your EEG data using independent component analysis, or ICA. First, I'm going to talk about what the process actually entails. I'm going to describe it, and then I'm going to go into BrainVision Analyzer and show you how you can actually implement it. So what is ocular correction? Essentially, we want to remove the activity that we've recorded that isn't from the brain, and it actually has to do with our eyes moving and blinking throughout the task. So when our eyes blink or move, then our facial muscles contract, and that has an electrical signal that we're going to be picking up, and we want to remove it while maintaining as much of the actual neural activity, which we're interested in, as possible. So there's a couple different ways we might go about doing this. When you actually record the data, you can always tell participants to try and blink less. But there are some issues with that too. So you're all of a sudden introducing a new task, and now people have to keep in the back of their heads, oh, remember, don't blink. And people might have different abilities in being able to not blink, so that's going to introduce a confound. Another solution is to maybe remove all of the data surrounding these blinks, but blinks are pretty common, even as you can see from this, like, I don't know, 10-second interval here. So we would lose out on a lot of the data. And not only that, but people are going to blink more often depending on certain traits, and maybe those traits are going to act as a confound now. So the idea is that we want to remove the electrical activity caused by eye blinks and movement while maintaining as much neural activity as possible, while avoiding some of those confounds that can be introduced from other methods. All right, so what is the solution using independent component analysis? Well, the way that we go about this is that we want to break down the signal that we record into lots of different independent components or independent sources. And then we want to find those sources that we've just broken the signal down into that closely resemble a blink. And then we want to remove those from the sources and then reconstruct it to get back at our signal. So to make that a little less confusing, I'm going to show the common example that's given with this, which is a cocktail party problem. So imagine that you have one or two microphones, however many microphones set up at a party, and you're recording the audio. So that audio is going to be a combination of all the different sources that you're picking up in the room. So there might be music going on, there might be 5 different people talking, and what you record is going to be a combination of all of those sources or independent components, as we're going to call them now. So each of these components is independent from one another, and when we record, we're combining, we're summing together all of those sources here on the left in a certain way to get here. Okay, and if we had 3 different microphones, each of them would be a different combination of these sources. Let's say your microphone was right next to the stereo. Obviously, this music component is going to have a greater weight to it, right? It's going to make up more of this signal than the voices, and vice versa. So what we want to be able to do is break down the signal that we've recorded into sets of components, and we also want to know how we can get from these components to the signal that we recorded by knowing how much of each signal we have to weight and we have to combine in order to get at this signal. All right, and just to reiterate, so the solution to ocular correction with ICA is that we break the signal down into all these independent components. We find the ones that we think are the most like what blinks look like, and then we remove those from the data, and then we reconstruct the signals using those weights that we've figured out. All right, so in order to understand this a little better, I'm first going to describe the process of actually going from sources to signals, and then from signals to sources. So what you see here, first on the right, is what we actually know. So we've recorded from a bunch of different channels. Let's say that there's 7 here. So 7 channels or electrodes, and we have the electrical activity over time at each of those. So X1, X2, X3 is just the electrical activity recorded over time at a certain channel, X1, X2, X3. So what we want to get at, we have this, is we want to know what the independent sources are so that we can see which of these might be blinks, and so we can remove it. So in order to get from here to here, we have to have what's called a mixing matrix. And first, I'm going to show you how you can actually get from sources to the recordings, because that's a little more intuitive, and then I'll describe quickly how we go about it the other way. So when we have a bunch of sources, think about these as maybe different regions in the brain, or if you're thinking about the cocktail party, different people talking. So what we want to do is know how to get from those sources to the signal that we've recorded. So all we need to know is how much of each signal to combine when getting to this one. So what we use for that is called a mixing matrix. And all this is a certain weight that we're going to apply to each source to get to each signal. So for instance, if we wanted to know how to get to the signal recorded from channel X1, then what we're going to do is look at the column in this mixing matrix. This column is X1, this column is X2, this column is X3. We're going to look at this column, and we're going to take this weight and multiply it by each of these sources. So you can see here, this is source, so source 1, source 2, 3, 4, 5, 6. So we have this weight. We're going to go signal 1 times source 1 times this weight, plus source 2 times this weight, plus source 3 times this weight, and you can see it down here, and that's going to give us X1. So this mixing matrix is just a simple way of knowing how much of each source we have to combine in order to get to the signal that we recorded. Now, if we want to go the reverse direction, if we want to get from what we have to the sources, so signal to source, then what we do is use an unmixing matrix, it's called, and that's simply the inverse of this mixing matrix. So now you kind of understand how we can get from signal to source and from source to signal. But the question remains, how do we come up with this mixing matrix? There's a ton of different ways that we could just describe a mixing matrix to get from random sources to here. How do we choose one so that we can be confident that we're getting at these independent sources that in some way could add together to give us our signals? So that's essentially the question. And in order to do that, in order to solve this mixing matrix, we're going to use some type of algorithm, and we're going to vary this mixing matrix. So we're going to try a bunch of different possible combinations, and we're going to find the matrix that minimizes a certain measure that we're using that we want to get at in our sources. So in the sources, so in the independent components we want, what we want to know is that all of them are independent from one another. So as the name suggests, what we're doing is that we want to represent the signals we recorded as independent components. So all we need to do is have some way of measuring the independence of a set of sources, and then we can just vary this mixing matrix kind of algorithmically until we find one that maximizes that independence, right? So we want to find the mixing matrix that maximizes the independence of our sources, and that's the one that we're going to go with, and we're going to choose this is how we represent the signals we recorded as independent components. So in order to measure independence, what we're going to be using, there's a lot of different metrics you could use, but we're going to be using mutual information. So this is just a way to say these sources have X amount of independence from one another, and we're going to try and solve this mixing matrix so that it gives us the sources that are maximally independent. Obviously, it would take a long time to do this, weight by weight individually. So there's these algorithms that can do it very quickly, such as the fast ICA, which we'll be using in BVA, or Infomax. There's lots of different ones. All right, so again, just to reiterate, we want to get from independent components to signals that we've recorded so that we know which ones to remove. So in order to do that, we need to solve this mixing/unmixing matrix so we can get from one to the other. And to do that, we just find the matrix that maximizes independence. And we've measured independence with mutual information. All right, so now that you understand kind of the process of independent component analysis, you really know how it can be used to take out these eye blinks or these eye movements that we see in the data. Okay, so in order to describe the process in a little more detail though, I'll go through the 4 steps that we're actually going to do in the BVA. So the first one is that we look at all of our data and we highlight the blinks. So you can see here on the right, this is kind of what a blink looks like, and we're just going to use some characteristic about the nature of blinks, the fact that they go up really quickly. We're going to use that to figure out where in our data should we look. This isn't necessarily saying this is 100% a blink. It's more so a first pass to understand where in the data should we be looking so that we don't have to look at the entire data, which would be computationally inefficient. So we do a first pass of the data using some measurement of what a blink is. In this case, we're going to be using the mean slope algorithm, which just looks at how high of a rate of change there is of that blink. So we're going to highlight where in the data our blinks are. So now we've got all of our blinks. Then we're going to apply that ICA, the independent component analysis process that I just talked about. So we're going to apply that algorithm to figure out how we can represent all of our signals as sources. And we're going to do that. We're going to transform all of our signals into independent components. And then what we're going to do is measure how similar each of those components that we've looked at is with the blinks that we already highlighted in step 1. So in order to measure the similarity between a component and a blink, what we're going to do is use an eye channel that we've set up when we recorded the EEG. So we're going to use our vertical eye channel for blinks and our horizontal eye channel for eye movements. And we're going to look at the time windows that we specified in step 1. So maybe, 35 to 35.4 seconds in this example at channel VEOG, or whatever channel we use to measure that vertical eye activity. So we're going to look at how similar all of our components are with the vertical eye activity for these time windows. Okay, and by similarity, we're just going to choose some measure. In this case, it's the shared variance between two signals. So we're going to have some measure of similarity, and we're going to apply that for every one of our components with the blinks that we've identified. And then we're going to set a certain threshold, and we're going to say when a component shares a certain similarity, in this case, a percentage of variance with the eye blinks that we already highlighted, then we're going to say that is a blink, that component is a blink or an eye movement, and we're going to set its weight to 0. So now the component's weight is 0, and we're going to reconstruct the actual data. And when we do that, now we've removed that part that was hopefully solely a blink or solely an eye movement, and now we've got the data without that blink or eye movement in it. So that's kind of the idea behind it, is that we decompose our signals into independent components. We see which ones of those are most similar to blinks, we remove it, and then we reconstruct. All right, so I'm going to go ahead and show you what this actually looks like in BVA. So here I have open a set of trials. I believe there's 25 trials here. And I can flip through them like this, and you can see immediately that lots of these channels have distinct blinks in them, or I would assume these are blinks just based on the way that the nature of their activity, really. Like, that's kind of how it works. We just assume they're blinks because they show that distinct waveform. All right, so we can see by looking at these segments that there's lots of blinks, and now we want to apply ICA. So I'm going to go into where I am here and click transformations. And right here, ocular correction, ICA. I'm going to do automatic mode selection. And the difference is when I talked about looking at the similarity between blinks and components, that process where we choose a threshold of similarity is an automatic one. You can also do this semi-automatically where you go through each blink yourself and kind of determine, rather than having a similarity threshold, you determine yourself based on both its topography and its amplitude, and you decide yourself whether or not it's a blink. I'm going to be doing the automatic process here. All right, like I said, in order to detect where blinks are in this data, we're going to use the mean slope algorithm. And this is BVA's way of identifying when these upticks occur. And I'm going to specify the channels that I've been using for vertical activity and horizontal activity. I've already done that here, but you can do that as well, and use a common reference. And I'm going to apply this to all of my channels. Now, something I should note here is that when we do independent component analysis, the number of sources, so the number of components that we can actually identify, is dependent on how many spots we recorded from. So if we recorded from 128 channels, then we can use a maximum of 128 components. Now, there's one assumption, is that those components are independent from one another. So what that means is that if you have done any interpolation, so let's say you edited a channel before and you removed it and recreated it as a sum of 5 channels that were nearby, then all of a sudden you've lost that assumption of independence. So you can't now use that channel as a component. So now you have to subtract 1 from the number of components you can use. So if you had 128 channels and you interpolated one, now you can only have 127 components. And you'll see when I actually run this that BVA is going to pop up and tell me this is the maximum number of components you can have based on the channels that you've interpolated. So just accept, because that's the assumption that we have to meet in order to use independent component analysis. But anyways, I'm going to apply this to all channels and click next. All right, so here I have 25 segments, and each one is about 6 or so seconds. So I would ideally use the entire data that I have in order to construct that mixing matrix and figure out what my components are. So this is what that is asking me of. Do I want to use the entire data set to come up with these matrices, or do I just want to use a certain interval around the blinks that I've identified? Now, this is entirely dependent on the amount of time it's going to take you to run this. Really just how much time based on the size of your data. So how many trials you have, how many participants maybe, how many electrodes on the head you have. You're gonna have to run this once using the whole data and see how long it takes. Because ideally, we're going to get stronger results if we can use the entire data set, but sometimes it's not efficient. It takes just too much time to actually do so. So I suggest at first running this with the whole data set, seeing how long it takes, doing the calculation for, okay, how much time would this add for all my participants? And if you are able to, then use the whole data set. If you're not able to, for some reason you've got hundreds and hundreds of channels and 1,000 participants and it would just be too much, then you can use the interval measurement. And I would just use the suggested values that BVA provides for us. It knows based on the number of components or the number of channels you have, what amount of data it should take. So what size interval it should be using around those blinks, how much data it should be using to come up with these components. I would suggest just using their suggested values. But for me right now, just because I'm doing a video and to save time, I'm going to also do this. But again, I suggest you use whole data. All right, so what algorithm do we want to do to solve that mixing matrix? Do we want to use Infomax, bias Infomax? I'm going to be using fast ICA today, and we're going to be using restricted. We don't want to bound the number of blinks, so we want to have as many blinks as there are. We don't want to set, the first 60 blinks, identify them and then stop. We want to use all of our blinks. And again, I would just use the suggested values for convergence and the number of steps that BVA provides here, just to make things simple. All right, now this, because I'm doing automatic detection, I'm going to have to choose a threshold for similarity between the components that I've identified and the blinks that I've identified. So here, 30% is, I guess, the standard kind of value that's accepted. So we're just going to leave it at that. But of course, this might be something that you want to play around with if you find that you're removing too much of the data or too little. So I'm going to leave it at 30%, and I'm going to do that for my VEOG, so my vertical eyes, my blinks, and my HEOG, so my eye movements. I'm going to use 30%. And there's a couple different metrics that you can use to define similarity between components and blinks. I'm going to be using the relative variance, like I talked about in the PowerPoint. I'm not so interested in the actual matrices themselves, so how we got from components to sources, but if you are, then you can write it to a file and go and examine that yourself. Maybe if you want to use it for more analyses in MATLAB, maybe, but for now, I'm just going to not write it to a different file. All right, so I'm going to click finish that. You can see it's going to go through the steps. It's going to identify the blinks, and then it's going to try and solve that matrix so that we can go from sources to signals and back and forth. Okay, here I got the pop-up that I said I would. I wanted to compute a number of 128 components, but the data has only rank 122, which means that 6 channels have been interpolated and don't meet that assumption of independence. I'm going to go ahead and click yes. I don't want to violate that assumption. And this is the part that takes the longest, computing that matrix, running that fast ICA algorithm. And again, this is the part that you're going to have to know, can I use the entire data set, or will I have to use just a certain interval around the data? Feel free to skim ahead in the video while I wait for this to load. All right, so now that that's finished loading, you can see I have this node that just popped up here, says Ocular Correction ICA, and you'll also notice that compared to where I just was, blinks have immediately, oops, let me go back to the first trial, have been removed. So this is the ocular correction. This is the data we put in before. So obviously these strong blinks here, and here they've been removed. So that's essentially a way to just give yourself a double check and say, okay, there was actually some blinks removed, something went on here. And you can also go through and skim the data to see whether or not it captured all of what you might look at and think are blinks. So this is, again, the data before we applied ocular correction. You can see that there's lots of blinks. Some trials don't have any, but lots of them do. Some have more than one. And here's the ocular correction. So I'll just skim through these trials, and you can see that this looks like it captured most of the blinks. Awesome. So that's it. Hopefully now you understand how you can implement independent component analysis in BrainVision Analyzer and what that process does and how it can remove these artifacts that might have been induced from eye movements and blinks.